Okay, good morning everybody. Okay, so the last thing we did Tuesday, we talked about interferometric sensors, and I mentioned the two types, the ones based on the classical Michelson interferometer and the ones based on grating interferometers, which can even work without a laser, which is a big advantage. So I brought to show you, this was the first grating interferometer encoder which came on the market. It came on the market around 1983 or something like this, 82, 83, and it was quite a revolution because from the outside it looks just like a normal encoder, but if you look at the specs, this has a quadrature output like any other encoder. Each quadrature, as you see, it's written on it, is 81,000 pulses. So if you have quadrature, it means you actually get 4 pulses per sine wave. Because if you recall, all these encoders, in order to tell direction, have a quadrature output very much like a stepper motor drive waveform. So if you have 81,000 of those, you actually get 4 transitions per cycle, okay? So basically this means that you get 4 times as many pulses as cycles. It's exactly like a stepper motor, backwards, right? So this encoder had 81,000 of those, so altogether it had 324,000 pulses or transitions in this little teeny thing, because it uses much averaging. Because unlike a regular encoder where you have to focus the beam to read a line, the grating interferometer, you can take the grating, in this case it was a round grating, you can take the grating and illuminate it with a very large spot because you don't need to focus. And this one illuminates it with 2 large spots on opposite sides of the diameter in order to get rid of eccentricity. So each spot covers thousands of lines. So because of that, you get averaging of thousands of lines. So not only does it very high resolution, it has amazingly high accuracy. So this encoder was an order of magnitude improvement over any other encoder which existed. So today, most people don't need such a good encoder. But if you really need it, these encoders are beyond comparison to normal encoders. The only disadvantage is that the way they were sold commercially, they were limited to 300 RPM. Because they were designed actually to be used in robot joints. The idea of the company, Canon, which came out with it, that if you put it in joints of a robot, you can have very, very high positional accuracy at the tip of the robot. So a robot joint doesn't have to move fast. So they limited the electronics to 300 RPM, but there's no reason to, because if you put a fast photodiode, it can go unlimited RPM. I know because I even changed one of those 30 years ago. I took out the electronics and changed the electronics to run 10 times faster because I needed it at a higher speed. So I know there's really no trick to make it go as fast as you want. Because as I mentioned before, any photodiode can work at a megahertz, and if you put in a pin diode or anything, it can work at gigahertz. So all what it has to do at the end, there has to be 2 photodiodes which count light, dark, light, dark. It's no limit to how fast you can do that. So I'll pass it along just to see. Please don't drop it because it's an expensive thing. Okay, so this was the first interferometric encoder. Now you can buy them even driven with an LED. This one still had a laser diode from a CD player inside. It was powered by a 780 nanometer CD player laser diode. So I think we'll wrap this up. Because we have many things to cover, and we only have like 1 week left to talk about sensors. So the next subject I want to discuss is capacitive and inductive equivalence to the optical encoders. We talked about linear optical encoders, rotary encoders, shaft encoders. So these are very good, very reliable because you can use an LED. You can do some tricks with averaging, but they have one disadvantage. And the one disadvantage, they cannot be made flat. Because anything which has an LED and a lens and a beam of light cannot be made flat. And in some devices, there is a desire to make something very flat and compact. For example, this thing that all of you know, obviously it has some kind of a linear encoder, but you want to have it very flat. And there is not enough room actually inside to put a lens and an LED, or interferometrically there's just not enough room to do it. But there is two other types of encoders which are the equivalent of optical encoders, and the whole encoder can be made the thickness of a sheet of paper. And that's a great advantage. And these are capacitive encoders and inductive encoders, which actually work very similar to the capacitive sensors we talked about, an inductive sensor. So let's just describe them. And the other thing we'll cover today is something that I'm sure nobody here heard of, but it's one of the smartest ideas in sensors ever. And that's tellurometer. Has anybody here does anybody here know what a tellurometer is? Okay, I suspected that. So it's surprising. There is a type of sensor which is one of the smartest idea in sensing and the highest performance sensor there is, and nobody ever heard of it, which is a shame. Okay, although it has been manufactured for 60 years. So I want to spend the rest of the time to explain tellurometers, because the principle behind tellurometers is can be used in many other things with amazing performance. Okay. So first, capacitive encoder. So we talked before of capacitive sensor. We have two plates and measure the capacitance. But you can do something else. You can make an encoder which has a series of capacitive plates. And let's say they are placed on some pitch. It's called wavelengths. Okay. Now this is the stationary part. Now you have a moving part which looks the same. So this can be very long, and then you have a moving part which I'll draw in another color, but some green. Okay. So the moving part looks the same, but usually it's shorter. Okay, like this. Let's just draw three of them or four of them. Now, the moving part, these are all wired together to an output. This is the out. And the stationary part is wired that all the even ones are connected to one phase of a sine wave, all the odd ones are connected to another phase. So the way this is wired, let's just raise it. Okay, so the way the stationary part is wired, this is like a long strip. So we take all the odd ones and we wire them to phase 1. And let's draw it, say, a sine wave like this. And we take now every second one. Erase this line not to confuse you. We take every second one. This is the junction. And we wire it to an antiphase. There is phase 2. So this phase 1 and phase 2 at 180 degrees. Okay, so now we are looking what will come out here. So if it's lined up, okay, just one thing I didn't do right, because this should have just correct one thing. You can do it the way I drew it too, but it's easier to explain it like this. Let's say this just has two sensors and it has double the pitch. Let's say it has double. If this is lambda, this is 2 lambda. Okay, let's just explain this scheme first. So here are the moving plates. Okay, so if it's aligned the way it's aligned now, you will see phase 2 coming out. Because the plates are overlapping the plates of phase 2. They are not touching, they are capacitively coupled. Just overlapping. But since these are overlapping phase 2, you will get a sine wave coming out from phase 2. Now, if you move it 1 lambda, these green plates will be overlapping those, and the phase will change to phase 1. Okay? Now what will happen if you move it? If you move it just by, what happens if you move it by half a lambda? So in other words, what happens if the green ones will be moved that are exactly straddling two of those? What will you get? So you get half of this sine wave, half of this sine wave, right? Which are at opposite phases. So what do you get if you take half of phase 1, half of phase 2, add them together? 0. So basically, in this position, in the dotted line position, you get 0. So if I look what's coming out, and I start sliding the slider, okay? What I'll get is I'll get something which looks like an AM modulated signal, because I will get the carrier, which is a phase 1, phase 2 frequency, and when it lines up, it gets big. Then when it starts not lining up, I'll get 0. When it lines up again, I'll get big and then 0. And what I'll get some envelope, which is just like an AM signal. Now, this envelope sine wave is basically the movement, how fast I move it. The inside sine wave, what's called the carrier, is just the excitation. That's called the excitation. Okay? But there will be a difference between this sine wave and this sine wave. They will be in opposite phases. Because this comes when it's aligned, say, with the odd plates, and the second one comes when it's aligned with the even plates. So this will be filled with phase 1, and this will be filled with phase 2. So I will be able to tell, basically, if it's sitting here or here. Okay? So now, so now I have several ways to use this to measure. If I want to measure it as a normal encoder, okay, all I have to do is I have to run it through an AM detector. An AM detector is something which just takes the envelope of this, very much like we discussed in LVDTs, right? So AM detector is just a diode. If I take this signal and run it through a diode and filter it a bit, so here I'm getting an AM signal, but here I'll just get the envelope coming out. Okay? So that's the same as the signal from any other encoder. If I move it 2 squares, I'll get a sine wave. Okay? And so this is the same as an optical encoder. I can interpolate if I want and so on. I can make this quite thin, but there is some smarter ways to take this encoder and interpolate in a very, very good way. Okay? So the smarter way to do it is measure the phase, because it turns out that it's very easy to build a very accurate phase detector. And this idea, the fact you can make very accurate phase detectors, is behind the 3 technologies I want to discuss today, which is a capacitive encoder, inductive encoder, and tellurometers. All 3 rely on the fact that it's very easy to make good phase detectors. So if you have a sine wave, which is a reference, and you have a second sine wave, which is the one you want to measure the phase. Okay, so you can see all what you have to do basically is measure the zero crossing. Okay, and this distance divided by this, or this distance divided by the wavelengths will give you the phase. And now this is time. Time is very easy to measure accurately. You can have a digital clock running very fast, measuring this time, measuring the whole time, and you have the phase. You can even do it simpler if you just want a DC value which is comparable to the phase. All what you can do is you can take a set reset flip-flop, which is the simplest type of flip-flop, bistable. So here you have set reset, and you connect the reference, say, reference to set, and the second signal, and this is a sine wave, or the measured signal, let's call it signal to reset. And then you look at the output of this, it will give you a DC value equal to the phase, because the first one will set it, the other one will reset it. So you'll get pulses here, and the pulses will look like this. Here it sets it, here it resets it. As the phase becomes bigger, these pulses become longer. Okay? If you just take this and put some little filter here, to just put a low pass filter, you'll get a DC voltage proportional to phase. Right? So basically a phase detector is a 10-cent set reset flip-flop. Okay? And you can do digital, you can do more elaborate things with a high-speed counter, but if you just want to convert it to DC, you just take a set reset flip-flop and that's a phase meter. Now, what is surprising is that these phase meters, when you build them, are astonishingly accurate. And one reason of it, because there's a lot of averaging. Let's say you want to know the phase every tenth of a second. You want to update the phase every tenth of a second, but the carriers can be a megahertz. So now, in a tenth of a second, you're averaging 100,000 measurements. Okay? So that's part of the reason. There's other reasons which I wouldn't get into it. It is less sensitive to noise than amplitude detection. We talked about the FM versus AM, we just touched on it briefly. So there is some noises here. They will affect the zero crossing. The noise will affect the zero crossing, but it will average out very quickly. So altogether, it has good noise immunity. Say if there is clipping here, it would make no difference. If there's distortion, it will make no difference. Right? So there's good noise immunity, there's high averaging. The short of the story is that for 10 cents you can make a phase detector which is accurate to a tenth of a degree, and a tenth of a degree is already 1 part in 3600. It's already not bad. But it turns out you can build phase detectors which are accurate to 0.001 degree with just a few bucks worth of components. Okay, now 0.001 degree, that is 1 part in 360,000. Right? Because 360, if you divide it into 0.001 degree, so that is actually amazing. 1 part 360,000, that's amazing resolution. So if you had a voltmeter to measure an analog voltage, it would mean 3 microvolt on 1 volt range. Now it's very difficult to make a voltmeter which can measure a volt to 3 microvolts. But here it measures phase to the same resolution. So what you can do is you can do other tricks. And the other trick is this. When you take two sine waves which have the same frequency and different phases. So let's say you take sine omega t, and then you take sine omega t plus phi, and phi is a phase shift. Now, when you add these two together, okay, what you get is you get a sine wave with a phase which depends on the proportions of this and this. So say if this is A amplitude and this is B, and you add them together, so you can do the math, and what you get is if A equals to B, okay, if A equals to B is simply sine omega t plus phi, which is sine A plus sine B, right? So you get sine A plus B over 2. So basically you add these two together, divide by 2, so you get a phase shift of phi over 2. But if you add them together not 1 to 1, so let's say you have a sine wave of this size, and this is A, this is the first one, and then you have a sine wave with a different phase but a different amplitude, and this is B. Okay, so this is 0 degrees phase and this is phi degrees phase. So obviously if this was much bigger than this, the result will have the phase of the larger one. Like you can see it visually. If one is much larger than the other, it will dominate the phase. But you can, at 1 to 1, if both are the same, you already know from the math, the phase will be phi over 2. Okay? So you can see that the phase varies continuously as a ratio of the proportion of the two sine waves. Okay? Now what you can do is you can do this in a different way. You, instead of feeding in antiphase, say you can feed it in quadrature. Okay? So that phase will move from 0 to 90 continuously, and you can make, and it would not cancel out. You will not get a 0. Okay? Because now if you feed it one phase and the antiphase, when it's exactly half and half, you get a 0, and that is very good if you just want to count cycles. because it gives you the best signal. It goes to maximum and to zero. But if you want to interpolate phase, you can do some more refined tricks and say if you take this with quadrature, if you can take sine omega t and so a of this, and then plus sine omega t plus 90. So it's two quadrature signals. Okay, and this is b, but you make a and b equal 1. You basically take 1 times 1, then you adding up two sine waves which are out of phase, but that's basically the same as adding sine and cosine. So this is the same as adding sine omega t plus cosine omega t. Never mind the plus or minus, because I'm not relating to that. You have a sine wave or cosine wave. Now, when you add a sine waveform, okay, so when you add a sine waveform and a cosine waveform, you get a waveform which, so you can, so basically you add a sine waveform, and now you add to this a cosine waveform, which I'll draw here. Okay. First of all, you have quadrature signals. If you look at both signals, you have quadrature signals which you can use to tell the direction you are going, and you can take the phase in between. Right now, the phase in between will be 45 degrees, but if it varies, if the A and B vary because of where you are on the plates, the phase will continuously vary. Because if one is sine and one is cosine, the amplitudes will depend how much you overlap the plate. When the plate overlaps completely one, you'll only get sine. When the plate overlaps completely the other, you'll get cosine. If the plate is half and half, you'll get sine plus cosine. Okay? So basically, you continuously vary the A and the B, and constantly the phase is changing. Because, is that clear to everybody? If one plate is driven by sine, one cosine, you are adding a sine and cosine depending where you are. If you're in the middle, you're adding the 1 to 1. If you're here, you're adding more of 1. So the phase is continuously changing. So now if you take this output, connect it to a phase meter relative to the reference, you have a very good interpolation of the position. I know I went maybe a little bit too fast on that, but I'll cover this again with the inductive type. So you can do many tricks here. So you can either count returns to 0, or you can measure phase by having two phases and measuring the phase. If you measure the phase, you can interpolate this distance easily to 1 part in 10,000, and if you make a very good phase detector, you can interpolate this distance or the phase to hundreds of thousands. So it means that this pitch doesn't have to be very fine, because the phase will allow you to interpolate it to a very fine degree. So if you make an optical encoder, if you want a high resolution optical encoder, the pitch of the encoder has to be very fine. If you want a high resolution encoder based on phase measurement like this pitch could be maybe 5 millimeter, and you interpolate it. Let's say if this was 3.6 millimeter, and you interpolate it to this, so the resolution you will get, 3 millimeter is 3000 micron. Okay, and let's say you interpolated it to 1 part in 300,000. So in theory, if you had a perfect phase meter which can do this, which exists, you had a 3 millimeter pitch capacitive encoder, the resolution you get is going to be 1/100th of a micron, 10 nanometer. So think of it, it's quite amazing that you have such a crude pattern, 3 millimeter pitch, with a very good phase meter, and you end up with a resolution of basically 1/100th of 1 micron, 10 nanometer. So this is the power of the combination of a phase meter and capacitive or inductive encoders. Like in theory you could do that with light, but in light it's very hard to measure the phase of the light, because the light is such high frequency you cannot measure the phase of the light. The only way to measure the phase of the light is by interference, because interference is a crude phase meter. When the antiphase you get dark, when it's in phase you get bright, in between. So these interferometers in a way work as phase meters, but you can't, it's very hard to interpolate the phase of the light to this accuracy. But if you replace the optical encoder with a capacitive or inductive encoder, you can pick the frequency. So you pick a frequency where you can build a very good phase meter. Typically for very high precision instruments you would pick like 1 megahertz, because if you go too high it's hard, there's noise, there's other problems. You go too low, you don't have enough averaging. So you pick a frequency which gives you enough averaging, enough meaning tens of thousands of cycles per measurement, but not too high that it's difficult to build a perfect phase meter. So bottom line, these things operate at anything from kilohertz to megahertz. If you go much above a megahertz, it's hard to build such a good phase meter, so you don't gain. You gain on the averaging, but you lose on the phase meter. So bottom line, they work at not very high frequency, and they rely on the phase meter. Okay, so exactly what I drew here, you can do inductively. And inductively what you do is, instead of having capacitive loops, okay, you have little coils, and the coils can be printed on a printed circuit. So the coils are actually as flat as the capacitive electrodes. Both these types of encoders can be printed very, very flat, because it's just two printed circuit boards almost touching each other. So if I made an inductive encoder, you do it a little bit different. You print a pattern like this on a printed circuit board. And I think this will be a bit more clear here. Okay, and you run it with an AC source. Now you have a slider which slides over it, which looks the same. So this is just a line printed on printed circuit board. Again, the pitch is lambda, and the lambda doesn't have to be very fine. So the pitch of the line is lambda, and this typically is a millimeter. It doesn't have to be very fine. Now you have a slider which looks like this. It takes the other colored chalk. Okay. Anyway, I lost. Oh, here. Okay, so now on this you have a second slider which looks like this. Let's say we draw it and have, okay, like this, and this is the output. This is output. Okay, so let's draw the current momentarily. Momentarily the current, say the current is coming this way. Momentarily the current here is up, here is down, here is up, here is down. So if let me just think for a moment if everything is correct. Yeah, okay. Yeah, so if the slider is sitting the way it's sliding now, you get a transformer, because if you have two coils parallel to each other, the magnetic field from this will couple the two. You get a transformer, you'll get a signal. You put in this AC, you'll get a sine wave coming out. Okay? Now, if you move the slider to sit in this position, okay, what do you think you'll get? In other words, if the slider wires are halfway between the conductors of the fixed scale, what will you get? So just think of two conductors. Just think of this portion. So if two conductors, one carries current here, another carries current here, and you put a third conductor in between, and you see what voltage does it pick up. So what does it pick up? Zero. Because whatever it picks up from this will be cancelled out by this. Because they're equal distance, both have an induced field. The fields cancel out actually in the middle. There'll be no, okay? So you pick up zero. Any way you look at it, because of symmetry, if this goes up, this goes down, the current here can go neither up nor down because of symmetry. Okay? So you pick up zero. Now what happens if you move the slider half a wavelength, if you move it to here? So let's say the slider was here, and just look at one line, it's easier to see. So let's just talk about one line of the slider. The slider was here, and we picked up a sine wave. Now we move the slider to here, and we know we pick up 0 because it's symmetry. Now what happens if you move the slider to here now? Just think of one line, it's easier to see. Okay, so what will you pick up if the slider was here? Antiphase, because if this was going up, this current was going up. Here the current is going down. If you put the slider here, it's going down. Okay? So now the thing starts looking familiar. It starts looking exactly like this. Okay? So if you do it this way, okay, you get a sine wave, as you move the slider, you get a sine wave which gets maximum when it lines up, goes down to 0 when it's in the middle, and becomes maximum again. Okay, but if you check very carefully, if this is phi, this is 180 degrees out. This is phi plus 180 degrees. Exactly like with the capacitors, you get an envelope. If you just want to count whole cycles, all what you have to do is run the envelope to an AM detector. But if you want to be smarter, you can actually look at the phase, and what you do then, you put typically 2 loops with 2 phases. Instead of 1 loop, you put 2 loops. One is driven by this, and one is driven by quadrature. That's a typical arrangement. So now you have a second loop here. Okay, and this is driven by another generator, which is, if this is driven by phi, this is driven by phi plus 90. And by the way, it doesn't have to be 90, because any 2 angles will work, but it's just, traditionally it's done with quadrature, because then you can also sense direction and all kinds of things. Okay, so again, it's the same thing. You have 2 loops, you end up the contribution of the 2 loops, and you continuously measure the phase. And sometimes the slider also has 2 loops and all kinds of other tricks that you can do. But the main principle is, you don't just look at the AM, which works, but it's a simpler way to do it. You actually look at the phase inside. Okay? And the reason why you still need the AM is the phase will repeat itself every cycle. So if you just look at the phase, you wouldn't know how many. I mean, you could indirectly, but it's easier to do it that you count whole cycles, and then you know how many complete cycles you traveled, and then you look at the phase, and the phase interpolates the last cycle. Or you can just look at the phase from the beginning and integrate. Keep counting the changes with an integrator and know where you are. So you can do it many different ways, but the main idea is here. In both are the same. The main idea in both is that you have a very coarse pitch, you get fine resolution by measuring the phase. Okay? And there's many variants on how to interpret that. Okay. So, as a good example of these things, I'll show you 2 devices. Okay, so all of you know that. Okay? But very few, actually, I find out very few students know how it works. They all use it, but nobody was curious enough to open the dead one to see how it works. So I did it for you. Okay? So I have to activate the projector again. Okay, now we have to wait. The projector died. Okay. So we have to wait a minute. It'll come back. So okay. So in the meantime, I'll explain what this thing is, and I'll pass it along. So this thing is a high performance servo motor, which instead of a regular optical encoder has this encoder on it. Okay. This type of encoder is known under the trade name Inductosyn. This is a trade name that the company which came out with it first, Ferranti, gave it. So that's still known as an Inductosyn encoder. You can still buy those. Most people never heard of them, but they're actually very good encoders. The advantage of those over optical encoders, again, they can be made very flat, and they can give you very high averaging, because you can have many of these loops averaging, like in a circle. In a circular encoder, you can do here easily what I mentioned is not done in optical encoders. I mentioned optical encoders, people actually don't average the whole disk. But in an inductosyn encoder, the pattern runs like this around the whole disk, so you actually average the whole disk. So this gives you a lot of averaging, very high accuracy and resolution because of the phase meter, and it's very flat. So that's actually a much better encoder than an optical encoder for high performance. Its only disadvantage that in theory an optical encoder can work at higher frequencies, because here you need a carrier frequency which is much higher than the modulation frequency. And in an optical encoder, the carrier is the optical frequency. But in reality, you'll never be able to run a shaft so fast that an inductosyn wouldn't be able to follow. Because if you make the carrier here 10 megahertz, and you make, if it's 10 megahertz carrier, you can easily have an envelope which is 100 kilohertz. And even if you have 1,000 lines, or say 100 lines in an encoder, it means 1,000 rotations per second, which is 60,000 RPM. So if you do the calculation, you see that it's not a real limit. It's a theoretical limit, but in reality, this encoder is actually much higher performing than an optical encoder, and therefore it's used in precision machine tools and sometimes in servo motors, which need very high performance. So you can't really see the traces because it's covered. The slider covers the fixed part, but you can see from the end that it's a PC board, and you can see from the end that there is some rotating PC board on top of a stationary. You move this and you see. Okay, one downside it has, that you need electrical connection, which is actually a downside. So if the motor is rotating continuously, you need a rotary transformer or something to bring out the electrical connection. This was a servo motor which only went back and forth, so it's just a wire came out. You didn't need a rotary transformer. So that's an inductosyn. Okay, now what's this? Oh, sorry. Okay. Okay, so now we have to wait another few seconds for the projector. Okay. You have in the course notes, I know I went a bit quickly through this, in the course note, not in the video, but in the course notes, you have diagrams of that and explanations, and with better drawings how these things work. Okay, so if this wasn't clear, please refer to the course notes. There is one page on inductosyn, and there is also a tellurometer, which we'll explain next. But in a nutshell, what we are talking about in both cases, we want to get to a condition where moving the slider changes the phase of a sine wave. Because the phase is so easy to measure accurately that once you get that, you build a phase meter and you're done. Okay. So what I wanted to show you, as I said, most of you use these things, but very few of you are curious enough to open it. So I'll show it to you here and then I'll pass it along. Now I disassemble it so you can see the slider and you can see this. So it's falling apart, so when you pass it along, hold it together. So what we have here, okay, so this is a simple type. You can see there is two electrodes. There is a bottom electrodes and there is a top electrodes, and I'm not actually sure which phases this uses, so because it's hard to tell. But in general, you have two scales and then you have a slider, and in order to increase the resolution and to average more, the slider has many lines covering fewer lines here, so there is some kind of averaging taking place. I'm not quite sure about the algorithm here, but if I turn it over and I look at the slider, which I'll pass along, and you'll see the slider here has much finer lines than this. Okay, so I'm not sure if the attempt was to do some Vernier effect or the effect was just to average, but altogether one thing which may be why they did it this way, they didn't want an electrical connection to this part, because usually both parts need an electrical connection. Okay, one is excitation and one is pickup. So the way it was done here most likely is the excitation is capacitively coupled as well. Okay, because you can have a strip which capacitively couples the excitation, then you have no wires at all to the moving part. You can do the same in Inductosyn, and that's what's called a rotary transformer. You can have one coil which is just to couple. Okay, so I suspect what they did here is one set is just coupling the capacitive current, and the second set picks it up from here. Okay, so I'm not, as I said, it's hard to really know the exact scheme unless you reverse engineer the chip, but altogether it's, in principle, it's a capacitive encoder with, to save the wires, capacitive coupling of the excitation. Now, you can see an older one, and the second one is an older one, and that older one is actually inductive. And the reason you can tell it's inductive, you can't see it, but when I pass it along you'll see it. When you look at these circles, you see they're actually loops. So when I'll pass it, have a look at the bottom at these little circles, and then you'll see what happens. There is little circles which are actually loops, and then they are connected to some other circles, to some other loops. And what this is, it has in the middle a track which picks up the excitation and distributes it to odd and even. If you look here, you see this one has a loop every period. The top one has odd loops. The bottom one has the even loops. Because you see this one goes to the top, this one goes to the bottom, this one goes to the top. So what this is exactly what I drew on the capacitive drawing, but done inductively. It has a set of pickup loops, and the pickup loops distribute the signal to odd and even loops. Now you have a slider which picks up the odd and even loops, adds them, and measures the phase. So the bottom one is done more like the classic encoder, and I'll open the slider and you'll see. Taped it here. Okay. So here again, the slider has higher resolution, and you don't see much. First, because it's small detail. Secondly, it's coated. The printed circuit boards were coated to prevent shorting together. So both the capacitive one and the inductive one have an insulating coat. So here I scratched off some of the coat, and you can see three big areas, but inside the big area you see finer loops. So the middle area lines up with this. It's just a transformer to couple the excitation, and the top and bottom pick up the signal. Okay, so now I'll pass it along and you can have a good look. So this is the inductive. I'll pass it on from this end and have a good look so you can see the loops on the inductive, and this is a capacitive. Okay, now can somebody think what is the advantage of inductive over capacitive, or is there any advantage? If you have two dial calibers like this, and you can buy them for the shop, one is capacitive, one is inductive, is there any advantage to one over the other? Both have the same accuracy. So then you always start thinking about this immunity to the non-measured variables. Is there something else in the shop which could affect it, which you don't want to measure? Let's say what happened, pardon? Magnets. Okay, so magnets will affect the inductive, but the inductive works on AC. And because it works on AC, it's not sensitive at all to a fixed magnetic field. But if you had an AC field, like near a motor, it could be affected a bit. Not much, because it's very close, the loops are very close. But it's true. So AC magnetic fields will affect the inductive one more than the capacitive one. But let's say what happens if water gets into both of them? Because when you work in a shop, you have coolant. The machine tools have coolant. So let's say you measure on a machine tool and it splashes with coolant and the coolant gets under the slider. What will happen to the capacitive? What will happen to the inductive? Which one will suffer from water getting into it? Capacitive, because inductive doesn't care at all. The mu r of water and mu r of air are the same. So if you take the inductive one, put it under water, it works exactly the same. The capacitive one drop of water, it doesn't work. Because we talked about it in the first lecture. Okay? So actually the inductive one is better, but it's a little bit more complicated to make, so none of the ones you buy today are inductive. So the first 10 years of digital calipers were all inductive, because the people who designed them thought about it, that inductive would be better, but then they thought about it, nobody will know the difference, and they switched to capacitive, which is a few cents cheaper, which is a shame, because inductive is much better. But then, if you have a very good look at these two calipers I'm passing along, you'll notice something else. You'll notice that in the capacitive one, the electrodes are equally spaced. All along the capacitive one, it's a fixed pattern of electrodes. If you look at the inductive one, you'll notice that the loops, these loops have slightly different pitches. So in other words, if you look along the pattern, you'll see that these lines slowly start tilting because the pitch of the top loops is slightly different than the pitch of the bottom loops. Very minutely different pitches. And on the capacitive one, it's not. Now, this is a trickier question. Can somebody guess why on the inductive one you have actually two different pitches, which are very slightly different? That's harder to guess. Okay, so this question leads us to the next subject, which is the tellurometer. Because so far the way I explained all these encoders, they are incremental. Incremental meaning that if you turn off the power and turn it on, the encoder doesn't know where it is. Now you can make an absolute encoder, which when you turn on the power knows where it is. By the way, you can do the same with an optical encoder. In an optical encoder, besides having one pattern, you can actually have an optical encoder which has a binary pattern which reads in many tracks the bits of a binary number, and that's called an absolute encoder. So you can build optically an absolute encoder as well, but it's complicated. Okay? But if you have a caliper, it is desirable. I mean, it's a feature that it always knows where it is even when you turn the power on. So the ideal type of encoder is an encoder that you don't need to go to zero position and reset it and say that's zero. Let's say you have a machine tool. So most machine tools you have to initialize. You have to take the carriage, move it to zero, and then it picks up the zero, the index, and says zero. And from that on it's calibrated. It just counts fringes, okay, or counts sine waves. But it's nice to have an encoder which always knows where it is without having to move to zero. It's especially nice when you want to make some distance measurement device and you can't go to zero it. So if you want to make a device which looks at the wall and tells me the distance to the wall, but I can't go to the wall and push a button and say that's zero, because I want to just to look at the target without having to go there and say it's zero. So we talked about interferometers. An interferometer cannot do that. Interferometer is very, very sensitive to incremental movements, but it doesn't give you an absolute reading. Because when I set up an interferometer here and I have a mirror on the wall, there are millions and millions of sine waves between me and the wall. The interferometer just measures the last sine wave. So it gives you a very high resolution over the last wavelengths of light, but I don't know the absolute distance. Okay? So there is basically two classes of distance measuring devices. There are distance measuring devices which are absolute, like an LVDT is absolute. If I leave an LVDT a certain position, I turn on the power, it'll give me A and B signals. I don't have to zero anything. Okay? That's called an absolute encoder. But a linear optical encoder, unless I go back to the index and reset it, is incremental. Okay, all the encoders I showed you so far here are incremental. So the question is, can one build an encoder which will have all the advantages of what I described, like very high resolution, probably based on a phase meter, very high averaging, which means very high accuracy, but is absolute, so I don't have to zero it, so I can measure distance to objects without having to go and reset. And we'll know where it is on power up. Okay, so it turns out you can, and that's what a tellurometer is. So the best way to explain a tellurometer is actually give you a practical question, and this will show you intuitively how a tellurometer works. So let's say you have a tape measure. Just erase this.
Can you tell us why they
Yes.
use a pitch line?
Sorry, say it again?
You asked the question about the very pitch line.
Yes.
Did you answer it?
No, because you'll see in a minute, because I want you to think about it, because I want you to remember how a tellurometer works. I want to build up the excitement, asking a lot of questions, so hopefully you'll remember how it works. Because from my experience, the retention of the students is amazingly short. So it's but this is a very, very important principle, so that's something you should remember. So, to make you remember, I'll give you a practical question. You have the standard tape measure, okay? This is your standard tape measure, and you have on one side inches. This is inches, and on one side millimeters. That you have millimeters. And your tape measure is so worn out that you can't read the numbers. So the whole middle was worn out. All what's left of it is, say, a little line every inch or every eighth of an inch, and a little line every millimeter, every centimeter, it doesn't matter, but there are no numbers. Okay? Is there a way you can still use this tape measure? So I want an idea. How would you still use it if there are no numbers? So magnified, the tape measure looks like this. On one side it has this, on the other side it has this, and all the rest is wiped out. So my question is, how can you use this tape measure? Or can you? So let's hear ideas. I want to measure the distance to the wall with this tape measure. There's no numbers on it.
I guess you could use like the kind of like least common multiples between like the conversion of inches and millimeters.
Very good. Very, very good. Okay, so I'm not sure if everybody understood what you said, but since these two are not a multiple of each other, like millimeters and inches are not a multiple of each other, okay, I mean they will come back after a long time. They'll start after 254 or 127 millimeters, it will line up. If you look at these lines, there will be some place it will line up. Okay, and the first, and now since an inch is 25.4, the first time it will line up is at 127. So when you go to 127 millimeters, which is 5 inches, this line and this line will line up. Before this point it will never line up, because there is no other number here which is an integer number in inches and millimeters. Okay? Is that clear to everybody? Because just think of it, 25.4, 50.8, it's not an integer. The first time that the inch and millimeter will line up, where both are integers, is 127 millimeters. And then of course you know it will line up again. It will line up again at double Z, okay? So you have 254. That's obvious because it's 25.4 millimeters, so clearly at 10 inches and 254 millimeters line up and then line up again, okay? So even there are no numbers, if you look when the scales line up, the first time they line up, it generates a number, and you know this mark is 127. It's a strange unit. You're basically measuring it so many times 127 plus so many millimeters. It's not decimal, but it doesn't matter. You can still use it. But it's still a problem here because you can't tell if you are here, if you are a long times into the tape measure, a long way into the tape measure, and then you see it lines up here. So you know that this point is n times 127, but you don't know n. That's how you measure the wall. And then you can read, this is a wall, and then you can measure millimeters. These are inches, inches. Okay, so you know the wall is n times 127 plus some x number of millimeters that you can read, which is less than 127. Because at 127 it will line up again. Okay? So up to 127 millimeters, or up to 254 millimeters, okay, you can measure just because you know that reference. But if you are way into the tape, you don't know anything anymore because you don't know how many times it lined up, so you don't know the n. If you have a long tape, you are looking at the other end. Here is a place it lined up, and here is extra few millimeters. So you know it's n times 127 plus extra millimeters, but you don't know how many extra. But imagine that you would add another scale to this tape measure, and this other scale would be, instead of 25.4, let's say it will be another scale which is slightly different pitch than this or this, but different by very, very little. So let's say you'll end up here a scale which is a 1%, or let's say 0.1% stretched. So instead of 1 millimeter lines, you will have 1 millimeter and 1 micron lines. So the third scale will line up very, very rarely. Okay? And you can make it such a low difference that the third scale will never line up in the period you want. Okay? So basically, by using this principle, where the difference is very small, you can know what n is, because you can make the period as long as you want. So in the longest period, you will have less than one period in the whole scale. Okay, so what you do in a way is it's like measuring phase. I'm measuring phase between this and this. At some point, the phase returns to 0. Okay? Now, but when I'm here, I don't know how many whole cycles did I have. But if I had a period at the bottom, which is very, very slightly different, so it will never line up, but I measure the misalignment. The misalignment is a phase in a much, much longer period, which is less than one period. Okay? So let me explain at the bottom part again to make it clear. So let's go away from the tape measure example now, and let's talk about, you have two scales. One scale is millimeters, and the second scale is 1.001 millimeter. So each line is just a little bit, a micron farther, and as you draw it, at the beginning they look lined up. the beginning they look lined up, but as you keep drawing it, you notice that the bottom scale slowly starts getting out of phase, because the bottom lines each time are 1 micron more spaced. Okay? So after 1 meter it will line up. So this is 1 meter. Because 1 meter, this will be 1001 millimeters, and this will be 1000, this will be 1001. So actually not 1, but to make it more accurate, it's 1001 millimeters. At 1001 millimeters it will line up, because the top will be 1001 and the bottom will be 1000 times 1.001. It's 1001, so this line and this line will line up. Okay? Now let's say I'm somewhere in the middle of the scale and I want to know the absolute measurement. Okay? So I can tell by the misalignment. I can tell by the misalignment where I am in the absolute. Okay? But the misalignment is phase. We discussed. So now imagine these being sine waves. You can see where I'm heading. Okay, so if this is not a tape measure but a sine wave, okay, and it has this period, okay, and this sine wave here has a slightly different period, okay, and I have a phase meter. So if I send these two sine waves to the wall and get them back and measure the phase difference, okay, and if each one, of course, has to be measured against itself, because phase is a difference. Okay, so when I say measure the phase, I have two sine waves, which are the two references. I send them to the wall, I get them back, and I measure the phase against the reference. I don't know how many cycles I have between here and the wall, but what I do know that the phase difference is, say, 1 degree. So I can calculate what should be the distance, so the phase difference will build up to 1 degree. Okay? So what I can do is this. This phase difference will tell me in which cycle I am. But within the cycle I am, I can measure the exact phase of this to interpolate even farther. So I want to explain more clearly the last sentence. When each one of those cycles can be interpolated to a very high accuracy. We talked before to 1 part in 300,000. But it doesn't help me to interpolate this cycle very accurately, because I don't know how many integer cycles are in between. So when I take the example of sending a signal to the wall, I have two references. And this is f, and this is f plus delta f, which are exactly the same as these two scales, the inch and metric, or the same as two scales. I send them to the wall and get them back. Now I have a sine wave here, and I get back a sine wave like this, and I can measure very accurately the phase. Okay, so this, let's say this is 1 millimeter, and I can measure the phase to 1 part in 300,000, so I get phenomenal accuracy, but I don't know the integer number of cycles. Okay? I can measure the phase very accurately on the second one, but it doesn't help me because I already know within one cycle where I am. But what I can also do, I can look at this phase difference, call it phi1. Okay? And I can look at this phase difference and call this phi2. And by looking at phi1 and phi2, I can tell how many integer cycles there were between the beginning and the measuring point. Because when I start here, phi1 will be almost the same as phi2. Because when I start here, the two sine waves will almost be in phase. So when I measure phase difference on this, phase difference of this, I'll get almost the same answer within 1 part in 1,000. But as I move on, this sine wave starts getting more and more out of phase. Okay? So let's take a numeric example, because I see it's not clear. So let's take a numeric example. I want to measure a distance of 10 meters. Okay? And I have two sine waves. One sine wave is say 3 centimeter, and one sine wave is 3 point, let's take, okay, take 0.001 centimeters. Okay? So what will be the phases I'll get? Okay, so let's say 10 meters is already round pass, because when I go to the wall and back, it's double the pass. So let's say this is total length of pass. It's like this, it's double pass. So what phase will I get on the 3 centimeter? All what I have to do is I do 1,000 centimeters, which is round pass, divide by 3 centimeters. So I will get 333, and I'll end up with 1/3. So that is 333 whole cycles and 1/3 of a cycle. Okay? I don't know this number. I only can measure the phase. I only can see this. So this is 120 degrees. So what I'll measure with the phase meter, when I send the first wavelengths, and I have a phase meter, it'll come back and say 120 degrees. Okay? When I'll take the second phase meter and I'll send it, I'll get 1,000 centimeters divided by 3.0001. I took intentionally a very small difference so it will not wrap around. It will not build up an integer. Okay? Not build up an integer. So, okay, this is 1 part in 10,000. So this will be roughly, I don't have a calculator, but it will be roughly a 3.2, something like this. So if you did it with a calculator, you get, if somebody has a calculator, you can check the number, you get something like this. Okay, and then this will be 0.32 of a 360, so let's say it will be 119 degrees. Again, the numbers are made up. You have to check with the calculator to get the real number, but it will be something like that. Okay? Okay, can somebody check what do you get in phase? Anyway, just to put down the right number. So now, so all what I know, that I don't know this number, but I know that one frequency gave me 120 degrees, the other frequency gave me 119 degrees. Pardon? 116. Okay, good. That's better. Okay, very good. And this number is correct?
Yes.
Close enough, yeah. Okay, good. Anyway, so now, what do I know? So from this difference, I can calculate how many of these integers were, because each integer cycle gives me 1 part in 30,000 phase shift. So if I have 4 degrees phase shift, the difference was 4 degrees, I can calculate how many integer cycles I had. Okay? Because I know from here that I have the difference between the two is 0.001, another 0. Okay, so each whole cycle, the difference in degrees will be this times 360, because the difference between them is 0.001. So this will be a 0.036 degrees. So each time I travel one full cycle, the difference will build up to be this 0.006 degrees. Okay? Is that clear? So now, if the difference built up to be 4 degrees, okay, I can calculate how many integer cycles I had. Something doesn't compute here, because I should get 333 cycles. What did I do wrong? I have to divide by 3. The difference is this, the difference is this divided out of 3. So the delta is not 0.01. The delta as a fraction is 0.0001 divided by 3. Okay? Now it's correct. Okay, so I'm getting this. Please correct it. So per cycle, if the difference in wavelengths is 0.001, the fractional difference is 0.001 divided by 3. In angles, in degrees, is times 360 is 0.012. Okay? Now, since I have 4 degrees difference, I divide it by this number, and I know the number of integer cycles. Okay? So I divide this, I get 333 integer cycles, but I can interpolate the last cycle very accurately, because I know that the last cycle is 120 degrees, which is a third of this wavelength, to a very high accuracy. If I can measure this to a thousandth of a degree, so the last interval is 120 degrees, 0.000, because I can measure it to a hundredth of a degree, okay? Divide by 360 times the wavelengths, and this gives me, to submicron accuracy, that fraction. Okay, so this angle, the 1/3 of a cycle, is known to a very high accuracy. It's 1/3 of a cycle of a 3 millimeter wavelength, and it's known to 4 decimal places. So this is not just roughly a third. This is a third is 0.3333. So I can tell from one of the frequencies with very high accuracy the small digits. I know that it ends up with 0.333 centimeters. And from the difference divided by the buildup of the phase shift, I can tell this number. So altogether, I have a very, very high resolution. I have something which gives me 333.33 millimeters or centimeters. So basically, I can get 7 digits of resolution. And accuracy, not just resolution, because the phase meters, they don't have just a resolution, they have the absolute accuracy. Okay? So this is called a tellurimeter. And so this is an absolute encoder, because if I move the wall a bit, okay, this will change and the difference will change, and the difference will tell me the integer cycles. So if I turn on the power, and I read these two phases, I know the absolute distance without having to go to the wall and zero. Okay? Is that clear to everybody? Great. Yes?
Can this be done optically as well?
Pardon?
2 different wavelengths of light?
Yes. Can be done optically, and it turns out it was done optically before it was done electrically, and it was done, I'll tell you the name of the guy. It was done in England. It was called a fractional coincidence interferometer, and Rolt. It was done by a fellow by the name of Rolt in England, and he just didn't call it tellurimeter, he called it fractional coincidence interferometer. He used it to measure gauge blocks. So what he did, he took gauge blocks and looked at the interference with 2 different light sources. That was much before the lasers. He did it more than 100 years ago. About 100. He did it 100 years ago. Yeah, 100 years, almost exactly 100 years ago. So that was Rolt, and that was in the Standards Institute of England. And he used it to measure gauge blocks. He wanted very high resolution, but also absolute measurement. So interestingly enough, it was done optically before it was done electronically, and about 60 years ago it was done electronically at the same time, and then it was called a tellurometer. Yes, please.
What happens if your stretch doesn't cover your measured distance? For example, in this case, if we were trying to measure 3 meters.
Then you'll have an error, because you wouldn't know how many full coincidences you got. Right? It's the same problem as with the inches and scales. After 127 millimeters, you wouldn't know. I mean, if you have a distance less than 127 millimeters, you could look at the difference between millimeters and inches and know where you are, because you couldn't count the millimeters, but from the difference you would know the millimeters. But if you passed 127, you don't know how many integer cycles you missed. So this longest cycle has to be longer than the measurement range. But it turns out all what you have to do is take 2 numbers which are very, very slightly different. Okay, and then the points they coincide again would be many, many meters. Like in this example, you could see in this example we picked real numbers. We picked 10 meters, we picked 3 centimeters, which is a real number of the tellurimeters work at gigahertz. So 3 centimeters is a real number. Tellurimeters today work at less than 1 centimeter wavelengths, but traditional tellurimeters, 3 centimeter, That's, you know, that's 10 gigahertz. That's what tellurometers work in. So these numbers are real. 10 meters, 3 centimeters are real numbers. And you can see that at 10 meters, it was a long ways away from wrapping around. It was only 4 degrees difference. To wrap around, you need 360 degrees. So this will be good to up to 1 kilometer. These two frequencies we picked, or two wavelengths we picked, which are real microwave wavelengths, will give you unambiguous results to a kilometer. So, but what is amazing here is this, that you are getting 7 digits of absolute accuracy. So it turns out that a tellurometer today can measure a kilometer to much better than a millimeter. And that is quite amazing, because that is the limit. We'll talk about it later, but it turns out there is a rule of thumb that it's very hard to measure anything to better than 1 part in a million, except time. I think I mentioned in the first lecture that everything except time, the hard limit is 1 part in a million in measuring, and a tellurometer is 1 part in a million. Okay, and for a very simple, relatively simple instrument, which is about this size, it's a little box, the range of a tellurometer today is 50 kilometers. So you can send the microwave beam to something 50 kilometers away, get back the answer to within a few millimeters. And that's a basic instrument in surveying, when you want to do accurate surveys. Okay? And in sometimes you don't even have to put a target there, you can reflect the microwave from an existing spot. Other times you have to put a reflector. But sometimes you have like a column or a crane or a metal object, you point the tellurometer to it, and it gives you the distance to millimeters. Now I know there are also laser rangefinders, because there's a lot of laser rangefinders, especially in the military. You send a laser pulse and you measure how long it takes to come back. That's used to adjust guns and so on. But a laser rangefinder doesn't come close to this accuracy. Okay, a laser rangefinder over this distance will be maybe 50 ppm accuracy. A tellurometer will be 1 ppm. So this is one of the most accurate measuring methods there are. It is an absolute encoder. It doesn't need to reach, it doesn't need physically to touch the point of measurement. It's a non-contact sensor. But the same principle can be used in small sensors. And now you know the answer to the mystery why the inductive dial caliper had a non-uniform spacing. So now so I'm reminding you why this whole story was, that if you looked at this inductive dial caliper, I said that you had one row of loops and you had another row of loops, but the other row had a slight buildup of offset. And this is to make it an absolute encoder, because that's a tellurometer actually. The way these original ones worked is a tellurometer. Okay? So how do the new ones work? Because when you take the new calipers, which are a capacitive with a linear scale, and you just turn it on, it knows where it is. So how can it know where it is if it's a completely uniform scale?
Stores it in memory.
Pardon?
Stores it in memory.
But you may have moved it when it was off. Right? It turns off, but then you can move it, then you turn it on. How does it know where it is? Yes?
It has a little slant and they change the dielectric constant.
No, it wouldn't be accurate enough. Okay, the answer is very simple and very disappointing. All the new electronic measuring instruments never turn off. When it says auto off, they never turn off. The only thing which turns off is a display. Now that's a very bad thing, because that's why the batteries are always dead. When you take any one of the new instruments today, like a digital caliper, digital micrometer, whenever you take it out of the drawer, the batteries are dead. And the reason is because it never turns off. It just turns off the display to fool you, to think that it's auto off. That's a very nasty trick, but every make today of digital instruments just drains the batteries all the time. But the original ones with the inductive tellurometer actually turned off, and the battery lasted forever. Okay? Good. See you next week. I want back, pass it along.